For millennia, we have gazed upon the stars, certain that life requires the warmth and light of a sun. But in the deep, cold reaches of our own solar system, two small worlds, one orbiting the colossal gravity well of Jupiter, the other cradled by Saturn, are forcing us to rewrite the cosmic rules. We speak of Europa and Enceladus, worlds entirely blanketed in ice, yet worlds that may harbor liquid oceans more vast and ancient than any on Earth. These are the ocean worlds, existing far beyond the sun's viable heat, in perpetual, crushing night. The evidence for Europa's ocean is formidable, derived from the Galileo spacecraft's magnetometer data. As Europa sweeps through Jupiter's immense magnetic field, the saltwater ocean, being electrically conductive, generates its own induced magnetic field. This strongly implies a global ocean, estimated to be 60 to 150 kilometers deep, containing more than twice the volume of all Earth's oceans combined. On Enceladus, the proof is visible. Massive plumes of water vapor and ice particles erupt dramatically from deep fractures near the South Pole. The Cassini mission sampled these plumes directly, confirming the ejection of salty liquid water from an internal source. It is clear, liquid water exists, right now, just beneath the surface. But in this perpetual night, far from the sun's faint energy, what engine sustains this profound liquid promise? The power source is not distant, but nearby, born of celestial mechanics. It is tidal heating. Jupiter and Saturn, colossal in their gravitational force, maintain their icy moons in slightly elliptical orbits. As a moon's distance changes, the gravitational pull varies, causing the entire body to be constantly stretched and squeezed, a rhythmic internal kneading. This mechanical process generates immense friction within the moon's interior, and friction generates heat. On Europa, this tidal energy is estimated to be sufficient to melt the bottom of the ice shell. On Enceladus, the heat is focused intensely along the south polar fractures, fueling the geysers. This tidal energy is a slow, enduring furnace, sustaining liquid water for potentially billions of years, time enough for a nascent biology to emerge. But water is only one criterion for life. The next is a source of chemical energy, and for that, we must look even deeper. On Earth, the deep ocean floor is home to oases of life utterly independent of the sun. They cluster around hydrothermal vents, cracks in the seabed where superheated, mineral-rich water bursts from the planet's mantle. Here, life does not use photosynthesis. It employs chemosynthesis, drawing metabolic energy from chemical reactions between water and rock. The base of this food chain is microbes that oxidize compounds like hydrogen sulfide. The plumes of Enceladus hold the definitive evidence for this process on an alien world. The Cassini spacecraft, through its mass spectrometer, detected molecular hydrogen and silicon nanoparticles in the plume. The only known geological mechanism to produce both simultaneously is the interaction of hot water, above 90 degrees Celsius, with a silicate core. This is the unmistakable chemical signature of active, alkaline hydrothermal vents. Molecular hydrogen is a potent source of chemical energy that could fuel a lightless metabolism. The Cassini data suggests that Enceladus has all three requirements for life: liquid water, essential chemical building blocks, and a persistent geochemical energy source. For Europa, the evidence for hydrothermal vents is not yet direct, but the possibility of rock-water interaction is high, given its predicted silicate core. If life exists on these moons, it would be an extreme chemoautotrophic ecosystem, a testament to life's tenacity, proving that the universe is not just habitable, but incredibly resourceful. We do not yet know the final answer, but the next generation of space missions, like NASA's Europa Clipper, is already en route. Arriving in 2030, Clipper will perform nearly 50 close flybys, using radar to measure the ice shell thickness and a mass spectrometer to taste any plumes, searching for the telltale organic and chemical signatures of life. These missions carry humanity's deepest question into the ultimate frontier. Are we alone? The answer, if it exists, will be found beneath the crushing weight of the ice, hidden in a warm, liquid embrace on a world without a sun.